Hello, I'm Norman Wildberger. Today we begin the second part of this course on linear algebra. In our first part, 26 videos, we've gone over quite a few basic foundational aspects of linear algebra, generally from a geometrical point of view. In the second part, we move more towards applications, of which there are very many. Alright, so we're going to be talking about applications to geometry, to physics, field theory, calculus, solving polynomial equations, and maybe even some economics. Along with this application-oriented material, there will also be some more theoretical material on matrix algebra, determinants, eigenvalues, projective linear algebra, and perhaps some other things as well. So lots to learn. In my opinion, linear algebra is perhaps the greatest single contribution of the 20th century to pure mathematics. So if we think of the 17th century, say, as being the century of the development of calculus, and 18th century roughly as being the birth of analysis, and the 19th century perhaps as the century of geometry, I think in the 20th century it was linear algebra that really blossomed and extended its fingers in all directions. We see this reflected in the prevalence these days of linear algebra courses, which there's almost as many as there are calculus courses in undergraduate curriculum these days. The subject is intimately connected with lots of developments in modern physics and provides a language for talking about quantum mechanics and relativity and the Standard Model and many other things. And it also underpins lots of economics, theoretical economics, engineering, computer graphics, computation, and other things. So it's a very important subject with lots of applications. It really has been a 20th century development. Even within pure mathematics, linear algebra provides us with a very flexible and general kind of language to set up lots of other, maybe more advanced topics. For example, operator algebras, representation theory, harmonic analysis, various aspects of geometry, for example, algebraic geometry, and also lots of topics within algebra itself. The subject is really also a foundational cornerstone for classical Euclidean geometry and projective geometry. And these days, especially when we link it with the relatively new theories of rational trigonometry and the currently much more studied subject of geometric algebra, which arises from the work of Grassmann, Clifford, and Hestenes. So I sometimes like to call this GCH algebra. And these were going to play some kind of role for us in the second part of the course. When it comes to the foundations of Euclidean geometry, in the latter part of the 19th century, and then more in the 20th century, the logical weaknesses of Euclid's elements became more appreciated and well known. And people started looking around for alternative frameworks upon which to build Euclidean geometry. Okay, so the name of Hilbert is often associated with this program. And it turned out that linear algebra provides a very useful substitute for the axiomatic treatment of Euclid. And this is a major sort of motivation, I guess, for linear algebra's rise in the 20th century. And this is very much a point of view of the French school of Bourbaki. However, it's important to realize that foundational difficulties with the current theory of geometry via linear algebra still remain. These are due to the ambiguous nature of the continuum that we have. Problems of real number lines, which I've talked a lot about in other series in this channel. The role of lengths and angles introduce transcendental quantities, so that even though we would like to stay within the context of linear algebra and do things purely algebraically, nevertheless, these notions inevitably take us outside of the purely algebraic framework and make the logical structure unbalanced and weak. All right, so in this course what we're going to do is we're going to steer a cleaner and a much more logical direction. Okay. We're going to introduce a new and powerful approach to linear algebra as a foundational cornerstone for geometry by essentially using dot or inner products as a foundational device and using ideas of rational trigonometry. So there's going to be a lot of new things here that even if you've taught linear algebra for many decades, like I have, you will find some interesting and powerful new ways of thinking. And this will be especially important for students of the 21st century. So this is going to be very much a new way of thinking about linear algebra that I'm going to present to you. In the first half of this course, we've talked a lot about linear algebra and the connections with affine geometry. So we're very familiar with the idea of exploring geometry via equally spaced grid of lines in two different directions, say basis vectors E1 and E2, allowing us to use linear combinations of E1, E2 to explore and describe things that are going on in a vector kind of notation. All right, so when we talk about affine geometry in this kind of setting, we have certain notions. But there are other notions that we don't have. And at this point, it's going to be important to be very clear about the distinction between what we do have in affine geometry and what we don't have. So we have a notion of parallel lines. Okay? And we have a notion of translation. So for example, if we have this vector E1 there, then we can appreciate that the vector from here to here is a copy of E1. It's a translate of E1. It's really the same vector, and so the notion of translation is built in to the notion of equality of vectors. We also have a notion of area. Actually, to be a little bit more precise, we have a notion of relative area. Because once we have a grid plane like this, we can say that this little rectangle here is going to have the same area as this one. Same area as this one. And this allows us to compare areas. And we can also say that, say, this area here is 1/2 of this area here. I say relative area because there's no absolute scale. We cannot say that this little area here is exactly 1. Well, we could, but we could also say that it's equal to 2. So in affine geometry, we do not have a built-in unit for area, but we are able to compare the areas of two different regions, at least if they're relatively simple regions given by lines. We also have a notion of scale along any line. The fact that we can space out multiples of, say, E1 allows us to understand that, say, these points here along this line here are equally spaced. And we can use that as a ruler, if we like, to make relative measurements along this line. We also can talk about relative scale along a second line. Okay, but what we don't have in affine geometry is a notion of perpendicularity. So far, we have not introduced the idea of perpendicular lines. We also don't have a way of comparing sizes of segments in different directions. So although we can say that this segment is equal to this segment, we have no way of comparing this segment E1 with this segment E2 in terms of size. It may look like to us that E2 is maybe 1.5 times E1, but that's not built into affine geometry. So comparing segments in one direction and segments in another direction is something that we are not able to do. Something else that we don't have, very notably, is Pythagoras' theorem. We have not talked at all about Pythagoras' theorem, which is the most important theorem in geometry, and of course, actually the most important theorem in all of mathematics. And for example, we don't have notions of circles. It doesn't make sense to talk about a circle in affine geometry. All right, so there's something missing from our geometry that Euclidean geometry has. These are all aspects of Euclidean geometry. So a natural question is, how do we extend our view of affine geometry, of vectors, linear algebra, to include the ideas and the concepts of Euclidean geometry. This is going to be a very important idea. What do we have to do, and how is the best way for us to bring Euclidean geometry into linear algebra? Very important. So I want you to think about Euclidean geometry as being composed of, first of all, affine geometry, and then something in addition, which we might call metrical structure. We're adding something to affine geometry to get Euclidean geometry. And the natural question is, well, what exactly do we mean here by metrical structure? What kind of metrical structure do we need? Now, if I go around and ask most students at most universities around the turn of the 21st century what the answer to this is, I will probably get answers in terms of, well, we need notions of distance and angle. That is a very unfortunate development that students have been trained to think this way. So, no, no, no. Okay, this is not the right way of thinking about metrical structure in linear algebra. And I'm aware that this is going to be a challenge for many of you who have been indoctrinated to think sort of automatically that if we want metrical structure, we have to introduce distance and angle. But let me remind you that's not just Norman Wildberger who says that these things are not the right things. It's also Euclid. If you go back to Euclid and you look and you read the elements, you see that he avoids distance and angle. He does so for a very good reason, because he wants to avoid the logical difficulties that are associated with these concepts. So the challenge for us is to figure out a way of going in the direction of Euclid, replacing distance and angle with some metrical structure, which is, however, completely algebraic and fits naturally into the realm of linear algebra. It doesn't involve us having to bring in unknown or dubious concepts from outside of linear algebra. So the new answer, the better answer, is that what we need is, well, it goes by different names. A dot product, an inner product, a symmetric bilinear form, a quadratic form. These terms are slightly different, but they are all very intimately connected. It's really the same essential idea. And it's the idea that's behind these things which are the crucial ones that we're going to be needing in our development of metrical structure. And we also need some associated algebraic notions from rational trigonometry. So we're going to take the dot product, let's say, and we're going to do things with it that are motivated from rational trigonometry and that basically have not been done before, but clarify what's going on dramatically. All right, so the notions that we're going to be needing, at least at first, are quadrants and spread. And that way we're going to be able to introduce metrical structure in a purely algebraic way. Yes, yes, yes. Makes us happy to do that. Everything is going to be logical and clear, no waffling at all. So as a basic orientation to the approach that we're going to take, there's probably no better way than to go back to the fundamental theorem in the subject, which is Pythagoras' theorem. And we're going to look at Pythagoras' theorem essentially the same way that Euclid and the ancient Greeks did, which is quite different from the way Pythagoras is treated in most modern textbooks. Okay, so an adjustment, a mental adjustment has to be made. All right, so here's Pythagoras' theorem, essentially as Euclid stated it. We have a triangle, ABC. Here it is. And it's a statement about what happens when these two sides, let's say, AC and BC, are perpendicular, denoted by this little square there. Okay, if they are perpendicular, then there's a relation between the three sides of the triangle. And the relation is that if you build squares on those three sides, so on this side here you build a square, on this side you build a square, on this side you build a square, And then you take the areas of those three squares. Let's call them q sub a, because this side happens to be opposite a, q sub b, because this side is opposite b, and q sub c. So these three areas, q sub a, q sub b, and q sub c, satisfy this relation. Q sub a plus q sub b equals q sub c. So Pythagoras' theorem is a relation about three areas, the three areas of squares built on the three sides of a triangle. Now the modern student is introduced to this theorem in a different way. They are taught that the fundamental notion is the length of the side. Well, the length of the side is the square root of this area. And so Pythagoras' theorem gets restated as one length squared plus another length squared equals a third length squared. The problem with that is that taking the square root of this area is a transcendental operation. By that I mean that it's really an infinite operation that you are not able to complete in general in a finite amount of time. Your computer needs to run not for 10 minutes or even 10 years, and not even for 10 trillion years. It has to run forever in order to calculate a general square root. Okay, this is some kind of a fanciful idea that we can run our computers till the end of time and then extract an answer and say, oh, here's the answer. It's the square root of 17. No. That's not the way Euclid thought about it. And he basically didn't think about it for exactly the same reason I'm just telling you. Right? He realized that there were problems with the irrationalities of something like square root of 17. And he realized that the way to avoid that is to not think in terms of lengths, but rather think in terms of areas. All right. So students of mathematics, if you don't think about Pythagoras this way, please change your thinking. Right? Spend an evening in quiet contemplation of Pythagoras and try to change your way of thinking so that you think about Pythagoras as being sum of two areas equals a third area. We're going to use the term Q here because the Greek word for this process of building squares was called quadrature. And we're going to call this area the quadrants of this side. So the quadrants of the side is the area of the square built on it. And so the length, in quotes, would be the square root of the quadrants. That's why we're using Q's. All right, so this understanding of Pythagoras sets up the metrical structure for linear algebra. Okay? It's all important to understand Pythagoras in the right way. All important. And now let's view our plane in terms of the familiar kind of linear algebra approach, but we're going to adopt a more Euclidean point of view. So we're going to draw our axes now perpendicularly, and we're going to try to make our scales on the x and the y axis look the same, so that this length or quadrants is the same as that length or quadrants. Here's a vector A. Say a general vector whose point up here is the point xy, which means that this coordinate is x and this coordinate here is y. So in this case, x would be something like 3.5, let's say, and y would be 2.7, something like that. All right, so there is a right triangle here. If we drop a perpendicular from the point A, we have a right triangle here. And if we're interested in this vector A, that goes from O to the point A, this vector A, associated to it, we're going to assign a number to it. Right? And that's motivated by Pythagoras' theorem, which says that this square here, whose area is x squared, plus this area here, which is y squared, is necessarily going to be equal to this square's area here. So Pythagoras' theorem is telling us that the area of this square up here is x squared plus y squared, where x and y are the coordinates of A. So we're going to define the quadrants of the vector A to be, so here's a definition. The quadrants of the vector A is x squared plus y squared. So given a vector A, that's a number associated to it. So for example, if the vector is the vector 2, 3, then the quadrants of that vector is 2 squared plus 3 squared, which is 13. If the vector happens to be the vector minus 1, 5, that vector there, then its quadrants is minus 1 squared plus 5 squared, which is 26. If the vector is, say, the vector 3 halves, 1/5, fractions don't bother us. We can still square this thing to get 9/4, square this thing to get 1/25, get everything over common fraction and get 229 over 100. And if we have a vector that's, say, purely in the y direction, 0, 7, well, in that case, its quadrants is 49, which happens to be a perfect square. So if you were a 20th century linear algebra student, you would say, well, shouldn't we be worrying about the lengths of these vectors instead? Don't we need to take the square roots of all these things? Shouldn't we say that the length of this vector is square root of 13 and the length of this vector is square root of 26 and so on? Well, that's what you did back in the 20th century, but this is the 21st century. So we've moved on, haven't we? Yes. So now we recognize that the fundamental thing is the quadrants itself, and there's no need to pretend that we can take the square root of 13, which is something that in fact we can't really do unless we extend our number system via an extension field. Of course, this one here is a perfect square, so this one we could take the square root of. It does make sense to talk about the length of this vector. There's something quite different about the length concept of this vector and the length concept for this vector. Here it works, here it doesn't really work, except in an approximate sense, or if you're willing to go to an extension field, whatever that might mean. Okay, so this is a very important concept. We're going to see that this is an example of what we're going to call a quadratic form. It's an expression that's quadratic in the coefficients of a, x and y. X squared plus y squared, very pleasant kind of algebraic expression. It's going to play a big role for us in our metrical understanding of linear algebra. There's another very important thing that Pythagoras teaches us, and that's how to think about perpendicularity. Because the perpendicularity of the two sides of the triangle that Pythagoras is talking about is central to the theorem. And in fact, the theorem gives us a handle on what perpendicularity means. So here's a triangle, and I'm going to say it in sort of a vector form now. So we have one vector v1, and let's say it's the vector x1, y1. So now I'm using round brackets to denote a vector. And here is vector v2, x2, y2. The third side here, we could express this vector here, I remind you, as a difference between v2 and v1. So this would be the vector v2 minus v1. So in this triangle here, we could ask, when do we have perpendicularity there? When is v1 perpendicular to v2? Well, Pythagoras tells us. So Pythagoras tells us that v1 is perpendicular to v2 precisely when? Well, the area of the square built on this side plus the area of the square built on this side adds up to the area of the square built on this third side. And in terms of the quadrants that we've just defined, the condition is that the quadrants of v1 plus the quadrants of v2 equals the quadrants of v2 minus v1. That's a restatement of Pythagoras' theorem in this linear algebra framework where we're using this definition of quadrants that we've just defined. Okay, now this condition here, let's call it star, has a pleasant reformulation. Okay, let's have a look at it in terms of coordinates. The quadrants of V1 is x1 squared plus y1 squared. The quadrants of V2 is x2 squared plus y2 squared. What about the quadrants of this vector? Well, this vector is the difference between these two vectors, so its coordinates are x2 minus x1 and y2 minus y1. So its quadrants is x2 minus x1 squared plus y2 minus y1 squared. Right? The quadrants of a vector is the x-coordinate squared plus the y-coordinate squared of the vector. These are the two entries of the vector, and so we have to square this one, and add them together. So this condition star is just rewritten here in terms of the coordinates x1, y1, and x2 and y2. And now a little bit of cancellation occurs. If we expand these things out, on the right-hand side, we're going to see an x1 squared and an x2 squared appear, and a y1 squared and a y2 squared appear, and they're going to exactly cancel out with all this stuff on the left-hand side. The only thing that's going to be left is minus 2 times the product here, so minus 2x1, x2, and minus 2 y1, y2 there. So all of that will be equal to 0. Well, if we bring that to the other side, and we divide by 2, which we can do, then we get that this condition is exactly equivalent to this condition. Much simpler. x1, x2 plus y1, y2 equals 0. So this condition is a condition between this vector here and this vector here. v1 is here, v1 is 2, v1 is x1, y1, v2 is x2, y2. To test whether they're perpendicular, what you do is you compute x1 times x2 plus y1 times y2, and if that's 0, the two vectors are perpendicular. And it's precisely it when. So if this is 0, they're perpendicular. If they're perpendicular, then this quantity is 0. And here's the origin of the dot product. Okay, that's going to be the dot product of the vectors v1 and v2. That's going to play a very central role in the next few videos where we develop the theory of dot products, but not just in 2 dimensions, and not just in this particular metrical situation. Okay? So we're going to look at the dot product and its generalizations more next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.